Everybody is happy and we just need to move on. So I'm going to start talking about the questions of the test, and therefore we will switch the screen away from my face to the things that you like more. So today we'll have test 3 plus Laplace transform. So in test 3 we had 3 topics. That was method of undetermined coefficients, variation of parameters, and the third topic was Cauchy-Euler equations. That's it. Of course, all these 3 topics are going to be on the final exam. Question 1 was solve y double prime minus 3y prime equals e to the 3x plus x squared minus 3. So this is an equation that involves a non-zero right-hand side and asks to use a method of undetermined coefficients. In step 1, what you need to do was solve the homogeneous problem, which is done by using the Euler equation lambda squared minus 3 lambda equals 0, which solves as lambda 1 equals 0, lambda 2 equals 3. So you have 2 different roots. So the solution of the homogeneous problem is C1 e to the 0x plus C2 e to the 3x. And e to the 0x is 1, so that's C1 plus C2 times e to the 3x. So that's the solution of the homogeneous problem. Then you can go to step 2, in which you want to find the formula for yp of x. Yp of x, you look at that right-hand side. That right-hand side consists of 2 pieces. There is one piece with e to the 3x, and there is a second piece that doesn't have an exponential. This is a polynomial of degree 2, and here you have a polynomial of degree 0 in front of the exponential. For the exponential part, you have exponential 3x, so alpha is 3, and you check whether alpha is a solution of the Euler equation or not. Alpha equals 3, it is a solution. So you need to multiply by x the equation that relates to e to the 3x. And for e to the 3x, the polynomial being of degree 0, you just need a constant times e to the 3x. Then times x, because 3 is a solution of the homogeneous problem. That's it for this piece. Then you find the second one for x squared plus 3. The exponent that is here is 0 because there is no e. When there is no e, that is e to the 0x. So alpha is 0 there. And 0 is indeed a solution of the homogeneous problem. That's why we need to multiply the yp for this piece by x as well. It is done separately. And then we look at the polynomial that is here. It's a polynomial of degree 2, so you need a polynomial of degree 2. You don't drop terms that are between because you think you don't see them in that polynomial. All we care about is the degree of the polynomial. So that is a x squared plus bx plus c. Therefore, we have a x e to the 3x plus little a x cubed plus b x squared plus cx. So this is the polynomial that you're looking for. And now what you have to do is to take the derivatives and track the coefficients. So that's the third step. Yp prime of x, in this case, that's a, and then 1 plus 3x times e to the 3x, that's a derivative using the product rule, plus 3ax squared plus 2bx plus c. And then you get a second derivative. That's a, and then you take derivative here. That's going to be 3 plus another 3. I think that's 6 plus 9x times e to the 3x plus here 6ax plus 2b. So those are the two derivatives, and now you've got to track the coefficients. For the first guy, you have x e to the 3x to track, then you have e to the 3x. Those are the two equations for the first, for a. Then you take second derivative x e to the 3x, that's 9a minus 3. First derivative, a x e to the 3x, that's 3a, equals right-hand side of the equation, x e to the 3x is 0. And as said in the lecture, when you multiply by x, this first equation must give you 0 equals 0. And that's 9a minus 9a equals 0. So that's okay. That's why I put the check mark. So I have it correct. Now I go to e to the 3x and I collect also. So that's 6a minus 3. And then I go to the derivative, that is a, equals, and I go to the right-hand side of the equation, that's 1. So you got 6a minus 3a equals 1, and that leads to a equals 1/3. Now you go to the second part. You want to track the coefficients of x cubed, x squared, x, and the constants. So you go x cubed, x squared, x, and the constant 1. Go with x cubed. Second derivative x cubed, 0, there, minus 3 times first derivative x cubed, 0, equals 0 because there is no 0 on the right, no x cubed on the right hand side. Same as for the first piece, this must get you 0 equals 0 because you multiply the guess by x. And then you go to x squared. X squared, look at the second derivative, none of it, minus 3. Go to the first derivative, x squared is 3a, equals 1. So right there, you got a equal negative 1/9. Then you go to x. Second derivative, that's 6a, minus 3. First derivative, that's 2b, equals x on the right-hand side of the equation is 0 because there is no x there. So right here, you'll find b equals a equals negative 1/9. That's it right there, straightforward. Now you track the constants. Second derivative, 2b minus 3 times the derivative c equals right hand side minus 3. That's it. Now you need to solve this for c. So right here you get c equals 2/3 of b plus 1. And you solve here, send c to the other side, so you get this. So that's minus 227 plus 1, which is nothing but 25/27. So you get your yp of x equals 1/3 of x e to the 3x minus 1/9 x cubed minus 1/9 x squared plus 25/27 x. And the solution of the problem, y of x on the last step, equals c1 plus c2 e to the 3x plus x over 3 e to the 3x minus 1/9 x cubed minus 1/9 x squared plus 25/27x. Any questions? All right, so this is what was supposed to be done in question 1. Now let's look at question 2. In question 2, I just said, write down the formula for yp, and I explained in the lecture what that means. You don't need to solve for the constants, you just need to write down what formula would get you to find the constants. Question 2, formula of yp. So a, you get second derivative plus 2y prime plus y equals x e to the x plus 2x cosine of x. This is what the problem looks like. And we need to write down the formula of yp. So that's 2 steps problem. The first step, of course, you solve the homogeneous problem, which goes to the Euler equation, which leads to lambda 1 equal lambda 2 equals minus 1. So the answer, y of x, is c1 e to the negative x plus c2 x e to the negative x. So that's the solution of the homogeneous problem. And now, in the second step, we want to find yp of x. And that's yp1 plus yp2, because we have 2 pieces of the right-hand side that are different. So yp1 of x, that is for this piece, the exponent is 1 e to the x. Alpha is 1. Is 1 a solution of the homogeneous of the Euler equation here? In this problem, is 1 a solution of the homogeneous problem? Can you guys hear me?
Yes. I can hear
you.
Yeah, but nobody is answering me.
No.
Is something wrong today? People are not interacting as usual. So 1 is alpha, not a solution of the homogeneous problem, so we don't need an extra x. Polynomial here, n is 1, so it's a polynomial of degree 1, so that's ax plus b times e to the x. That's it, nothing else. Now yp2 of x, that is for this piece. And then here, you actually have alpha 0 and beta 1 because of cosine. So you got alpha plus I beta is I, and I is not a solution of the homogeneous problem, and therefore we don't need an extra x. But because we see cosine, the guess must have both cosine and sine. That's what was explained in the lecture. So we will see cosine and sine. Then we have a polynomial of degree 1, that's 2x. So we need a polynomial of degree 1 for each of them. So that would be cx plus d cosine x plus ex plus f sine x. That's it. So we got yp1 and we got yp2. So yp of x is ax plus b e to the x plus cx plus d cosine of x plus ex plus f sine of x. That's it. Nothing else to be done. Nobody asked you to find a, b, c, d, e, f. Question was find the formula for yp, and that's it. Now b, in part b, we had y double prime plus 2y prime plus 2y equals e to the x cosine 2x plus sine x minus 3e to the x sine x. So that's what the question is. And the answer follows the same steps as the first one. So first step, homogeneous problems, 2y prime plus 2y equals 0. Get lambda squared plus 2 lambda plus 2 equals 0. And that gives you lambda 1, 2 equals negative 1 plus minus I. And so the solution of the homogeneous problem is capital Y of x equals C1 e to the negative x cosine of x plus C2 e to the negative x sine x. So that's it. Now we want to find yp. And for yp, we have 3 pieces. 1, 2, 3. So the first one has cosine 2x and e to the x. So this is 1 plus 2i. 1 plus 2i is not here. Therefore, we don't need any extra x. So let me go ahead and just say what yp of x is going to be. No extra x for this first part. Cosine 2x and sine 2x must appear. Polynomial of degree 0. So that's going to be a e to the x cosine 2x plus b e to the x sine 2x plus, we hop to the second part. Alpha is 0, beta is 1, so that is I, and I is not a solution of the homogeneous problem, so we don't need an extra x. Polynomial of degree 0, so that's going to be c cosine x plus d sine x. Then we hit the third one, and that is e to the x sine x, which is very different from the first one. And that is going to be alpha equals 1 beta equals 1. So 1 plus I is not a solution of the homogeneous problem. Therefore, no extra x, also a polynomial of degree 0. So it ends as e to the x sine x plus f e to the x cosine x. That's it. That's final answer to that question. And nothing else to do. Any questions about this? Everybody is happy. All right. Then we had problem number 2, which was about the variation of parameters. So and for variation of parameters here, I had 2 y double prime minus y prime minus y equals 2 e to the x. This is the problem that we need to solve using the method of variation of parameters. First thing first, solve the homogeneous problem. 2y double prime minus y prime minus y equals 0. That's 2 lambda squared minus lambda minus 1 equals 0. You solve this problem. Use any formula that you want. At this point in this class, I think everybody must be able to give the right answer to this. So you can use a quadratic formula, you can use anything you want. So when you do that, you find lambda 1 equal 1, lambda 2 equal negative 1/2. So the solution of the homogeneous problem is capital Y of x is C1 e to the x plus C2 e to negative 1/2 x. And in the method of undetermined of variation of parameters, we call these functions y1 and y2. y1 is e to the x, y2 is e to the negative 1/2 of x. And so the system of equation that I request is C1 prime y1, which is e to the x, plus C2 prime y2, which is e to the negative 1/2 x equals 0. C1 prime, derivative of e to the x, plus C2 prime, derivative of this negative 1/2 e to the negative 1/2 x equals, and the right hand side we said must be what you have here divided by the coefficient of the second derivative. So that's 2 e to the x over 2. So that's e to the x, not 2 e to the x. So that's what you get. And then you get w, which is e to the x, e to the x, e to negative 1/2 x, and the derivative negative 1/2 e to negative 1/2 x. You get that here. That's going to be e to the 1/2 x, negative 1/2 minus 1. You get negative 3/2 e to the 1/2 x. That's what you get as the Wronskian.
Isn't it negative 3/2 e to the negative 1/2?
What?
Isn't it e to the negative 1/2 x instead of e to the 1/2 x?
E to the x times e to the negative 1/2 x is e to the 1/2 x.
Oh, never mind. Yeah, just kidding. I had it written down right.
Yeah, just be very careful with that, all right? So you got this times that, so it gives you e to the negative 1/2 x. It gives you e to the 1/2 x, not negative 1/2 x. So you get that, that's w, and then you get w, you get c1 prime equals negative y2f over w. That's the formula I gave you, negative for the first one. So that's negative y2 e to the negative 1/2 x times f, which is e to the x, divided by w, which is negative 3/2 e to the 1/2 x, equals. And there you can see e to the 1/2 x, when you cancel with this one, you have e to the 1/2 x times e to the negative 1/2 x, that's 1. So the whole thing you get here is 2/3. So that's what C1 prime is, 2/3. And that tells you that C1 is 2/3, C1 of x is 2/3 of x plus a constant when you integrate. Then you go for C2 prime of x, and the formula says this is y1f, no minus this time, over w. y1 is e to the x, f is e to the x over negative 3/2 e to the 1/2 x. So this is negative 2/3 e to the 3/2 x. And so you can integrate this to get c2 of x equals, when you integrate this thing, you get 2/3 over 3/2. So that gives you negative 4/9 e to the 3/2 x plus a constant. And so you get the final answer, y of x equals 2/3 x plus c1 times e to the x plus negative 4/9 e to the 3/2 x plus c2 times e to the negative 1/2 x. And you can simplify that. So this is 2/3 of x e to the x minus 4/9 e to the x plus, here you get c1 e to the x plus c2 e to negative 1/2 x. And actually, when you get to this level, you can combine these two into one, because negative 4/9 is nothing but a constant. So this whole thing can tell you that y of x is 2/3 x e to the x plus c1 e to the x plus c2 e to negative 1/2 x. But if you stop there, you still have the correct answer, or there you still have the correct answer. Any questions? All right, now we head into the last question, which was the Cauchy-Euler equations. So question 4, Cauchy-Euler equations. A was 4x squared y double prime plus 4xy prime plus y equals 0. Now to answer that question, you write the equation m squared 4m squared plus 4 minus 4m plus 1 equals 0, which gives you 4m squared plus 1 equals 0. So m 1, 2 equals plus minus 1 half I, which means the solution is y of x equals c1 x to the power 0 cosine of 1 half of natural log of x plus c2 sine of 1 half natural log of x. That's it. And the second question was 4x squared y double prime plus 4xy prime plus y equals 2 natural log of x minus x. And I did say that all these two things are part of the same question. I didn't need to ask you to solve that first part. I could just ask you to solve this, and you can't solve this without solving that. So I said, solve this question and use that answer to continue the question. But some people repeated the same question, answering it here and there, even though I said don't do that. So you didn't need to solve the homogeneous equation twice. It's the same equation. Now, in this question, you just need to report what you have in the first step. And I said the best way to go about when you see this is to transform the problem and go back to t with x equals e to the t, doing that transformation and just writing down the system of equation using the equation that you got there, 4m squared. So that's 4 d2y over dt squared plus y equals 2 natural log of t. Natural log of x is t minus e to the t. So that's it. That's the equation that you have to solve. And you already have the solution of the homogeneous problem. And all you need to do is to find yp. So yp of x in this case is, for 2t, it's going to be a t plus b, because 0 is not a solution of the Euler equation, which is here. And then plus c e to the t. Same reason, 1 is not a solution of the homogeneous of the Euler equation. So this is what you get. And then you take derivatives and plug them in and get what your answer is. So derivative is a plus c e to the t, and the second derivative is just c e to the t. And then you track the coefficients. T, for t, second derivative, it's 0, plus the original function, you have a, equals right-hand side of the equation 2. So you got a equal to, it's a very pretty easy one. 1, for the constant, you go to the second derivative, it's 0, plus the original function. You go to the original function, you got b. On the right-hand side, the constant is 0. So you got b equals 0. And then you go to e to the x, e to the t, sorry. Second derivative, it's c times 4 plus the original function. In the original function, it's c as well, equals the right-hand side. It's minus 1, the coefficient. So you get c equal minus 1/5. Pretty straightforward problem. Less than 5 minutes, you got it. So you get that yp of t equals 2t minus 1/5 e to the t which translates back to x as 2 natural log of x minus 1/5 e to the t is x. So y of x is the solution of the homogeneous problem, which was written right there. C1 cosine of 1/2 natural log of x plus C2 sine of 1/2 natural log of x plus 2 natural log of x minus 1/5 x. That's it. And we are done with the test. Questions? Any questions? Is there any question? No? All right. If there is no questions, then we are certainly going to head into our Laplace transforms to end the lecture. And this is chapter 7 that we are starting. So we are starting by the definitions. So we have for a function f of t, the Laplace transform when it exists is the function capital F of s. So when you take a function little f of t, you get a Laplace transform, a new function that is a function of s that is equal to the integral from 0 to infinity of f of t times e to the negative s times t dt when this integral converges. That's what we call the Laplace transform of the function little f of s. Example, if you have f of t equals 1, just the function that assigns the number 1 to every value of t, what's the Laplace transform of this function? Capital F of s is therefore equal to integral from 0 to infinity 1 times e to negative st dt. That's what the definition means. And then you compute this integral. That's e to the negative st over negative s, and then you take it from 0 to infinity. And now here we have a problem when we want to compute this. Because it is an improper integral, this limit infinity actually means that you're taking limit when t goes to infinity. You're taking limit when t goes to infinity. And so what you need to do is make sure that you select the values of s for which that limit is finite, because you want the integral to be convergent. Therefore, here, I'm going to say f of s is limit as t goes to infinity of e to negative s t over negative s, plus when you plug in 0, you get 1 over s. For this limit here, yes, check that again. For this piece, for this limit to be finite, when t goes to infinity, you need s larger than 0. Because if s is not strictly larger than 0, there's just no way this limit is going to be finite. It's going to go to infinity. If s is negative, e to the negative st is going to go to infinity, and you want it to go to 0. So the condition shows up by itself that your s must be positive. In what case, this is 0 plus 1 over s. So the Laplace transform of the function 1, that's our first computed Laplace transform of the function 1, is 1 over s for s larger than 0. Welcome to the new world. That's it. Now see example 2. And then I define f of t equals 0 if t is larger than 2 and 1 if 0 is less than t less than or equal to 2. So assume we have such a function that is equal to 0. So let me draw that function. So this is the function I'm talking about. From 0 to 2, the value of the function is 1. It assigns 1 to everything between 0 and 2. And after that, it goes back to 0. Heads back to this line. So that's the function. And want to find what the Laplace transform of this function is equal to. By definition, the Laplace transform of f of t is equal to the integral from 0 to infinity of f of t e to negative st dt. And please raise your head and listen. It is important to understand what the sign integral from 0 to infinity means. Otherwise, when you get such a problem, you get lost. Now, this means I move along the line from 0 to infinity, from 0 to infinity. What is the value of f of t every time I'm moving? You see, when I'm moving from 0 to 2, that's the value of f of t. When I cross 2, this is the new value of f of t. So anytime you have such a thing, which is called a step function, you need to consider the fact that on each of the subintervals, the function changes. So here, I'm going to move first from 0 to 2. And right there, from 0 to 2, the value of the function is 1 times e to negative st dt plus, then from 2 to infinity. But when I'm moving from 2 to infinity, the value of the function is 0 times e to the negative st dt. This is something very important that you need to understand, because if you miss it, then you've missed it all. Is this clear for everybody? Again,
Yeah,
when
that's
you find, when you want to find a Laplace transform, you're moving with t from 0 to infinity through all the values, and then you're reporting the value of the function on each of the intervals that you made. When it changes, you write the corresponding function in the corresponding intervals. Now, right here, what you get is integral from 0 to 2 e to negative st dt, because 0 times this thing is 0. This whole thing is going to be 0 no matter what you do. And this integral is nothing but e to the negative st over negative s, plug in 0, then 2. When you plug in 2, you get e to negative 2s over negative s, minus minus plus. When you plug in 0, you get e to the 0, 1 over s. So the Laplace transform of the given function is 1 over s minus e to negative 2s over s. That's it. Well, any questions? Now, in some of the questions that you will be asked to solve, you will have the question stated as use the definition. Use the definition to find the Laplace transform. When that is said, this is what I want you to do. Write that integral and compute it. Even if you know how to do it using something else, you need to know the definition. You need to be able to use the definition to find a Laplace transform. Because when you be asked to do that, anything else that you do will be worth 0 points. Is there any question on this?
Could you clear up why 1 over s is just positive and not negative?
We plugged in the boundary of integration. We first plug in this one, then minus what we get when we plug in 0. And the minus that is down there gives you the plus.
Okay, thanks.
You're welcome, sir. Anything else? Is everybody okay with this? All right. So that's where we are. So we move to the third example that I kindly ask you guys to find on. So example 3, f of t equals 2 if 0 is less than t less than 1 equals 3 if 1 less than t less than 4 equals 0 if 4 strictly less than t. What is the Laplace transform of f of t? I'll give you 5 minutes for that. Anyone with the right answer? Wanna try, Preston?
Yeah, I can.
Okay. Go ahead.
So your f of s is going to be uh, the interval from 0 to 1
Yep.
of 2 e to the negative st dt
Yep.
plus the integral from 1 to 4, 3
Yep.
e to the negative st dt
That's correct.
plus 4 to infinity, 0 e to the negative st dt.
That's it. Then what's the first one?
The first one is the antiderivative is going to be 2e to the negative st over negative s from 0 to 1
Yep.
plus 3e to the negative st over negative s from 1 to 4 and then plus 0.
All right. So I can guarantee you that it's always going to be as easy as this as I'm showing. But if somebody refuses to see it, then of course when the time comes and I ask the question, it will look like something new. And then we plug in the numbers here and we're done. So when you plug in 1, you got negative 2e to negative s over s. You plug in 0, becomes plus 2 over s. Because when you plug in 0, e to that is 1, and minus gives you another plus. And then here you have plus, you plug in 4, so that's 3 e to negative 4s over negative s. And then minus, and the minus here, that makes you plus 3 e to negative s over s. So, and you got negative 2e to the negative s, and then you got 3e to the negative s. They add to give you e to the negative s over s plus 2 over s minus 3 over s e to negative 4s. So that's what the Laplace transform of f of t in this case is equal to. All right? That's how you use the definition. Now, when you become a professional using the definition, there are things that you can do. There's a theorem that can be used. So sometimes we say use that theorem to give the answer. So you just give the answer without having to compute the integral. So first thing, the Laplace transform of t to the power n is going to be n factorial over s to the power n plus 1. And this is going to be true for any n larger than or equal to 0. So when n is 0, that will be t to the power 0 is 1. And of course, we know from the first example that the Laplace transform of 1 is 1 over s, right? So the Laplace transform of 1 is 1 over s. That's n equals 0. Factorial 0, 1. 1 over 0 plus 1, 1 over s. So that's correct. We did it. And so 2, Laplace transform of e to the at is going to be 1 over s minus a. So we can prove all these. We just don't need to spend time on it now. You can use it. If the question just says find the Laplace transform, you can use any of these things. So this is true for S larger than A. Then Laplace transform of cosine of A t, that's going to be S over S squared plus A squared. The Laplace transform of sine of AT is going to be A over S squared plus A squared. The difference between cosine and sine is that the top is S for cosine and the top is A for sine. And the Laplace transform of sine hyperbolic of AT is A over S squared. Guess what? Here it's going to be minus A squared. That's the only difference. And the Laplace transform of cosine hyperbolic of AT is S over S squared minus A squared. So the difference between cosine and cosine hyperbolic is in the denominator, minus versus plus. Same for sine and sine hyperbolic. The only difference is in the denominator, plus and minus. And these are the basic Laplace transforms that we want you to know in this class that you can use, okay? When we need you to use this, you can just apply the formula without having to prove it. But if the question says, use the definition to find, then you need to write that definition and do as we did in example 1 through 3. Here, like say, you find the Laplace transform of t cubed. I just go ahead and I say t cubed, it's n equal 3, so that's 3 factorial over s to the 4th. And 3 factorial is 3 times 2, 6 over s to the 4th. So I just give you that answer and say that is true if s is positive. Laplace transform of e to the negative 2t, oh, that's 1 over s plus 2, because a is minus 2. Laplace transform of e to the 3t, I said, hey, okay, that's 1 over s minus 3, using that number 2. If you ask me what's Laplace transform of cosine 3t, I say thank you, that's s over s squared plus 9, because a is 3. You ask me Laplace transform of sine of 4t, I say, oh, well, that's it, 4 over s squared plus 16, because a is 4. Any questions? Anyone has a question? All right, so talk about properties. So the Laplace transform of a constant times f of t is c times the Laplace transform of f of t. The Laplace transform of f of t plus g of t is the Laplace transform of f of t plus Laplace transform of g of t when they exist. Laplace transform of 3t plus 5 is 3 Laplace transform of t plus 5 Laplace transform of 1. Laplace transform of t, that's n equal 1, that's 1 over s squared. And Laplace transform of 1 is 1 over s, so that is 3 over s squared plus 5 over s. With this, I find the Laplace transform of 3t plus 5 without having to do anything. And you please use this to find for me this Laplace transform. Wanna try it again? Want to help us, John? Cooper?
I'm still working on it.
I am as well. Sorry.
We have anybody who has finished?
I have it.
All right.
Well, first I broke it down into 3 different parts. So for the Laplace formula for the 2e to the negative t, I got 2 over s plus 1. And then for 3e to the t, I got 3 over s minus 1. And then for the negative cosine 3t, I got negative s over s squared minus 9.
Over.
S squared minus 9.
That's cosine, not cosine hyperbolic.
Plus, I meant plus. My bad.
Okay. So that's it. And there we stop today. I'm not going any further. If you have any questions, ask me. If not, I'll see you on Thursday.
Thank you.
Thanks.
Welcome.